So now let's review the different types of caches we have. So we've talked about fully associative, set associative, and direct mapped caches. So fully associative caches are flexible. You can put anything anywhere. So you're not going to have data conflicting with each other because of its address. But they're really hard to search. You either have to have comparators for every entry, or you have to search them one entry at a time. Set associative caches are reasonably flexible. You can put data anywhere in a set, but not through the whole cache. But you have to search multiple places in the set. So this is reasonable speed and complexity. Direct map caches, you only have to search one location. That makes them very simple to build and can make them very fast. But the con is that data can only be put in one location. So if you have addresses that conflict, you can't keep both of those addresses in the data at the same time. Now let's look at how you actually build these caches. So we saw this for fully associative cache. We have our address, which has tag data in it, and then we have some bits to determine which byte within the word. So for this, we take our tag data, we use the tag data to compare with all the tags in the cache and all the valid bits and figure out if we have hits. So for a fully associative cache, we need to have a comparator for every entry in the cache. Direct map caches are much simpler. So for direct map cache, we have the same address bits, but now we're going to use some of those address bits to look at which block in the cache might have our data. That is, we've gone through and we've said that each address can only go to one block, so we can immediately go and look at that block. From that block, we get out the tag and the valid bit, and we only need one comparator to compare to see if we have a hit, but we can only put the data in one location. For a set associative cache, it's somewhere in between. So here we have an address, and again, we're going to use some of the bits of that address to choose which set we look at. But since the data can be anywhere in the set, we're going to have to take out the tags and the valid bits for every entry in the set, and we're going to have comparators for each of them. So for the set associative cache, we need a comparator for every entry, for every block we have in each set. So let's review the different types of caches. So direct map caches, address can only go in one block. So this is very easy to search, because it can only go in one place, but it's inflexible. For fully associative caches, the address can go anywhere. So it's very hard to search because you have to look at every entry in the cache, but it's very flexible. And in between, we have set associative caches. Here the address can go anywhere in one set, but it's fairly easy to search because you only have to look through a set, and it's fairly flexible because the data can go in multiple locations. So if you want to compare these, you can say direct map is inflexible, fully associative is complex, and set associative is really a good compromise. So most caches today are set associative. So let's take a look at some caches today. So we'll look at an Intel Ivy Bridge processor, a 4-core x86 processor, and a Qualcomm Crate processor, it's a 4-core ARM processor. So the Ivy Bridge processor has level 1 caches for data and instruction. They're both 32 kilobytes, and they're 8-way set associative with a 64-byte line. It then has a level 2 cache, which shares instruction and data. It's 256 kilobytes, also 8-way set associative, 64-bit line. And then it has a level 3 cache, which is 8 megabytes, much larger, and 16-way set associative. So if you look at this cache hierarchy design, you'll see that we have the same block size across the whole hierarchy. And the reason for this is it makes it much easier to move data between the caches. If we look at the Qualcomm processor, it has a level 0 cache. Data and instruction cache is very small, 4 kilobyte direct mapped caches. So these are direct mapped. That means they're very simple, but they don't work very well. And why do they do that? Well, this is what's known as a filter cache. It's designed to save energy for small pieces of code. And so here they want to have the most efficient, simple cache they can. Then they have level 1 data and instruction caches, which are standard 16 kilobyte 4-way set associative. And finally, they have a large shared instruction and data cache, which is 1 megabyte and 8-way set associative. And you'll notice that for both of these processors, as you have larger caches, they have higher associativity. That's because you're going to have more data over a longer time, so you want to reduce the chance of conflicts.